The length that we went through to solve this problem baffles me to this day. Like, it's one of those problems that you're just like, I can't believe we missed that.
Like, everything's hard about this in coding or even in just writing when you're so focused on the goal that you can repeatedly read over errors. You feel like you've read something line by line, but you've elided what's wrong with it every single time.
If we succeed, we'll be the first commercial company to ever go out to deep space.
I'm Brett Gibson, and welcome to HiBit, a new podcast where we do deep dives on the art of problem solving with engineers and technical experts from our community of early stage startups. In today's episode, we're sitting down with Jose Acain, AstroForge co-founder and CTO. AstroForge is an asteroid mining company. We dive into the holy shit moment when a space launch does not go according to plan. A HiBit is the most significant part of the binary representation of a number. In coder jargon, it commonly refers to the most important thing you need to understand in a given context. I chose to name this podcast HiBit because when faced with engineering problems, the first task is often figuring out which part of the problem most affects the outcome you're driving towards. Join me on this journey as we discuss thorny engineering problems with my guests and get into the weeds about how they solve them.
Hey, Jose, thanks a lot for joining today. I'm really excited
Brett.
to talk about what you're working on at AstroForge.
Yeah, thanks for having me. So AstroForge is, in short, asteroid mining. We're making critical resources available for use on Earth by going after asteroid mining.
And so where are you in that process? Are you already sending rockets into space?
Yeah, we actually successfully launched our first satellite into orbit, and this is the first in-space refinery ever to be launched, and we're doing demonstrations and testing on that now. So that's where we're at currently and planning for our first deep space mission. We will have been the first commercial company to ever go out to deep space as of October of this year.
Wow, that's amazing. I think we're going to talk about something hard that you ran into along the way. Like, everything's hard about this. So maybe you can set the stage about what are the cutting edge technologies that go into sending a rocket into space and refining asteroids?
Our key technology, what we're really developing here at AstroForge, is the ore processing system and really the refinery, right? So that processing system has to take in regolith, asteroid regolith from the surface, input it into a refinery. And this refinery extracts platinum group metals from this raw material. And then on the output of that goes into a reentry capsule. So that capsule goes back to Earth, lands, and we sell it back for use here on Earth.
I'm struck that refining ore and rocketry are fairly divergent domains. So perhaps you could talk about what is your expertise in and how did you end up tackling this problem?
My first foray into aerospace, I worked at NASA Ames. So I worked on a number of CubeSat missions going out to low Earth orbit and a couple of initial trade studies for spacecraft going to cislunar and beyond. It was a really amazing opportunity. But it was also a bit discouraging, right? So some of these projects that I worked on, people have spent years, like decades on these things. And you demonstrate this hoping to get a flight out. Back then, flights to space were few and far in between. They're very expensive. So some of these programs got canceled. And you would just see the faces of your coworkers and see them just kind of defeated. After all this hard work, they don't get to see this thing fly. And that was very discouraging to me. And I thought, as much as I wanted to continue on working in space, I didn't want to spend decades of my life working on something and not seeing it actually do the thing that it was meant to do. So I actually left aerospace. I was like, this is not for me. I'm a robotics guy. I definitely love seeing things in action and actually seeing it working. So I moved into autonomous vehicles. So I worked in the Volkswagen Electronic Research Lab, working on autonomous parking and self-driving cars. We built an autonomous Pikes Peak racer. It ran that race course, and it was amazing. But then I got an opportunity to work at a burgeoning launch vehicle startup called SpaceX. I was the deputy chief engineer under Hans Koenigsmann. He taught me a lot about rockets and spacecraft. And then I moved into Dragon Avionics, so actually assembling the vehicle, the electronic components of the vehicle. and then operating that vehicle as it made its way into docking with the ISS. So, space mining is very different than the current terrestrial mining, because the processes that are used here in the terrestrial world are definitely not applicable to space. As far as my experience and background, it lends itself to this asteroid mining venture, mainly because we have to make this refinery space qualified, right? We have to build essentially a spacecraft. So my experience really lends itself to working on this problem.
How do you approach figuring out refining? Where did you start? Like, who did you talk to? Like, how did you become an expert in that as well?
You typically start out with analyzing what the current solutions are. The current mining solutions take advantage of gravity, reactants, reagents, and big pools of material and leaching. And these things obviously we can't really take advantage of that in space. It's a much harder problem. So it's really starting from scratch, right? So we had to look into ways of separating material only using electricity. And working in a high vacuum environment. And that was really the two main requirements that we had to work with us, because in space there's not, you have vacuum for free, and all you have is battery power as of now. The people working on nuclear, but right now, solar power, batteries, great. Like, let's start there. We read some research papers, and we actually contacted one of the authors of these papers that did build a high vacuum, purely electrical system that separated elements. And that was really the start of the design of our refinery that we built. Working with him and understanding the physics behind this refinery, how it works, how we can optimize it to work in space, and how we can miniaturize it such that it's not a large system. Because on Earth, it's a very large system to use. And that's mainly because you have to generate such a high vacuum. For space, you get that for free. So I think that was really the starting off point for this company as far as the refinery goes.
Yeah, that's really interesting. Sort of leaning into the advantages of the environment as much as trying to innovate on what you can do. Could you talk about how you met your co-founder and how you decided to work for them?
It's funny. My co-founder and I had very parallel lives. He worked in the space industry in a launch company called Virgin Orbit. He left that company, and I think he wanted to do something other than space. He was kind of burnt out, right? So around the same time, I was done with SpaceX and was wanting something different, something more. And we met at a company called Bird Rides. And we realized we had a lot of the same friends. And
that's far from space.
Yeah. But it was a very odd, weird meeting point at a scooter company working on software and scooters. But, that really reignited both of our passions for space. I think when we were working at our respective companies before, we kind of lost sight of that. And after talking with him about, his passions and in space and exploration and pushing boundaries further and helping humanity out and doing good with what our background is and also what our passions are, kind of lent itself to the start of AstroForge. So that's really where it started.
Well, all right. So, as you know, like to talk about hard engineering problem that you came across while building AstroForge. So maybe you can just start by introducing what came to mind when I asked you the question. What problem came up that would be interesting to dive into?
My first thought when I saw the question of what is the hard problem, and I laughed when I read it, because asteroid mining is the hard problem, right? So where do we go from here?
Yeah.
Let's just talk about the company. But the problem that I eventually came to was a simple problem to solve, but a hard problem to troubleshoot, given the schedule and the task at hand. It's a mix of complexity, but an elegant solution, though I am embarrassed to say what the solution is, but you'll hear it soon.
So perhaps set the stage. What stage of the company was this? How long ago? Who was working on this with you?
About 3 months ago. Like I said earlier, our main tech is building up this refinery. And we successfully launched that refinery in the space, and we're getting data now from it and analyzing that. So that's really awesome. But that main tech that we're building is this refinery. So it is a payload that takes in that material, an asteroid-like sample, and extracts platinum from it. So we have this payload. Obviously, it can't fly by itself because it doesn't, it needs power, it needs the comm systems, it needs antennas and solar arrays. So we have to integrate this refinery into a spacecraft, into a satellite. That satellite portion of it is something that we purchased. So at this stage, we were just testing the refinery payload, the final flight integration of this payload before we integrate it onto the actual satellite bus, the satellite vehicle.
I guess real quick, in space terminology, payload is what you're setting up on the rocket. Let's define that term.
Yeah, so the rocket is what carries the satellite into orbit. The satellite bus is just the power and the communication system and the attitude control system to point the spacecraft towards Earth in order to communicate, or towards wherever, right? The payload itself sits inside or on the satellite bus, and that is either the scientific equipment, the cameras, if you're Earth observing. In our case, the payload is the refinery. So what we developed for this mission was the payload, which was the refinery. And our external vendor created the satellite bus, which was the power and the communication system. And SpaceX was the rocket provider. So those are the three big pieces when it comes to like the operations.
the three big pieces of refining in space. Cool. All right. So maybe you could repeat what you said about who was working on the problem with you.
One of our integration test engineers and myself, we're doing the final testing of this refinery payload before we integrate it onto the satellite bus. And those checkouts went great. And let me take a step back. The refinery consists of three subsystems. So there's a vaporization subsystem, which vaporizes the material that's in the refinery. Then there's the ionization, which positively charges these vapors. So we shoot it with a very high energy source. In our case, it's a microwave. And once it's ionized, we accelerate it towards a target plate, and we store it over a mass spec. So we take the elemental properties and leverage them. So iron in this case is magnetic. So we have these very high-powered magnets that curve the iron away, and then the platinum is what stays and collects on that target plate. So those are the three systems. It's the vaporization, ionization, and then the collection. Everything was working. It was great. We generated the plasma. The plasma is when it's ionized, and we saw feedback from telemetry saying like, yes, we've actually depositing material onto this plate. So great. Now we can move forward and integrate it onto the satellite bus. And that's amazing. So we did that. And once we did that, we did another check just to make sure that we didn't mess anything up. And that's the point of failure. So we sat there going, this is confusing. We literally just turned this thing on, and afterwards it did not work. The potential number of root causes or causes for that problem is very minimal, right? Like you just moved it from one place to another, bolted down, tightened some bolts, plugged in some connectors. There's really not much that can go wrong, right? So what we did was, I don't know if you're familiar with a fishbone diagram.
No.
A fishbone diagram is kind of is a way to collect or causes of a problem. So you start with like the high level subsystems, and within that, the failure cases within those high level subsystems. Mm-hmm. And then you select which is, you kind of validate each one, right? So we split it up into those three subsystems that I talked about earlier. And there's an extra subsystem called the ground support equipment, which provides the power to either the payload or the satellite bus to do the testing, because you don't want to use the internal batteries. You want to make sure that those are really safe for flight. So those are the kind of the four main fish bones where we dug into, and we split that up and triaged that.
And this is a common technique you've used many times in the past? Is it?
We've used this, but typically you have a big long review and you say, okay, great, let's write down all this. For us, it was okay, great. We understand what the fishbone diagram is. Let's real time solve this, and let's triage this real time.
The high level intuition for this diagram is let's isolate parts of the system so that we can know exactly what we're testing at any given moment.
Yeah, you isolate parts of the system, and then you write down how that system could fail, given the circumstances of which the failure happened.
And so stepping back a second, like the interesting point is they just weren't sure if they could solve a problem. Whereas here, you thought you had it solved and you kind of ran into a wall where suddenly it wasn't. Maybe talk a little bit about just your first reaction. Was this part of the process? Were you in a little bit of disbelief? What was the first thing that came to mind when this jumped up?
Because it was so late in the schedule and we had to deliver this and integrate it and get it on the rocket in order to launch. My first thought was, holy shit, right? Like, I don't know if you have to bleep that for the podcast.
Yeah. Had you taken this step for granted?
Taken what stuff?
Like, had you taken success at that step in the process for granted previously?
Yeah.
You just assumed? Okay.
Yeah, you just assumed it was just going to work, right? So it was a holy shit. But I think, my experiences in the past with SpaceX really lent itself to quickly removing the holy shit moment and moving it down.
Yeah.
I think the more holy shit moments you have, the faster reaction time you have after you. So it was a short moment, but it was like, oh my gosh,
you're a nerd too. Holy shit! Yeah, that makes a lot of sense. Okay, so back to the fishbone diagram. Like, what how did you proceed? What was born out of that process?
So we had a, let's go ahead and fishbone this and not have a formal review, but let's figure out, great, here are the subsystems, what could fail, and we split that up amongst our team, right? So the hardware team took on kind of checking the actual circuitry, the electronics and the mechanical portion of it to see if something has happened. The integration team took on the vaporization portion and did that check. And then the R&D team, the science team, took on kind of the microwave ionization portion of it. And I took on, and the integration team also took on the ground support equipment, and they kind of triaged that way, right? So everyone checked their subsystems. It was good. We're like, okay, what is still happening here? So the ionization guy, the science guys checked the microwave system. They checked the forward power versus the reflected power to make sure, okay, is this actually generating enough power for us to actually ionize these vapors? And yeah, great. Standalone by itself, that component was working. The vaporization, we stuck in a vacuum chamber. We vaporized the material. Is that vapor throughput what we expect? And yeah, we were seeing vapors. The throughput was great. The current was what we expected. Amazing. The target plate, the collection plate, was doing exactly what it was. It was negatively biased. The only thing left was the ground support equipment. And that was the first thing we checked. Let's check the actual voltages coming out of this like power supply. It was like, okay, cool. The power supply is giving us 12 volts, what we would expect. But the thing that we took for granted was that in that installation from the payload to the vehicle, the harnessing also changed.
Wait, sorry, what is the harnessing?
It's a set of wires with connectors on each end to plug into the satellite or the payload into ground support, so to a computer. So basically, the data and the power go through this harnessing. So we had one set of harnessing that we used before we installed it into the vehicle, and that was great. And then we had another set of harnessing that attaches directly to the satellite, and that is the part that we didn't check. We took that for granted, right? We just assumed the harnesses. We made the harnesses as expected. The problem was that the harnessing that we plugged into the flight unit was a little bit longer, and there was actually a significant power drop from the power supply into the input of the vehicle, into the input of the payload.
Wait, how much is a little bit longer?
It's by a little bit longer. This was like
a yard, or like
yeah, this was like, I would say probably I don't know, 50 to 100 feet longer.
Oh, wow. Okay,
but we didn't expect that big of a drop. And it wasn't necessarily the length. It was actually the pass-throughs that we used, and the pass-throughs were a very big gauge pass-through, so it was a very big drop in voltage. So our spacecraft was expecting, our payload was expecting 12 volts. What it was actually getting was more like 8 volts, and that was just underneath our DC to DC converter that is used for our ionization system.
And you had tested the voltage going into the harness, but not coming out of it.
So we unplugged the harness from the pass-through, and we checked it, and we said, that's 12 volts. And we took for granted, like, it's a pass-through. Like, that's not, it works. We've seen it. Like, we can see the system turning on. And just because the system's turning on doesn't mean that you're actually getting the nominal voltage. You can still have a system turn on and it's barely, it's in a state where it's not working, right? It's not nominal operation.
Were you aware of the variance in harnesses? You know, like, was this even on your radar as like something you should have known about? And
the variance in harnessing for sure I was aware of, but that was not, it was not a significant enough length. Like I'm used to dealing, big drops typically happens with, launch rockets in at least really long, like thousands of feet, like very, very large harness lengths, right? So we were definitely aware of it. It was I think the main thing was the pass through, but we just took it for granted that, okay, great. We kind of glazed over it because we did a simple check. And then we really focused in on the hard part, right? The hard part was the refinery. So that's where we thought that we would, because this is the novel technology. Of course it's going to fail, where there is the new tech that we've built up and not the simple tech that's a power supply where you just turn it on, or a set of wires where you just, like put it together. And,
I laugh because like I feel like around the house, like thinking things are broken and finding out it's the cord is like pretty common.
What happened? You like checking your circuit breaker?
But maybe you could say more about that. I think that what's really interesting there is that you were very deep on a hard problem. So your intuition about what was wrong perhaps was centered around what was difficult previously. Is that accurate? Is that where your head went to immediately? Like what was your gut reaction of what was probably broken?
Yeah, that was absolutely the gut reaction. The gut reaction was, this is a difficult problem. Asteroid mining is difficult. The refinery is difficult.
It couldn't be the cord.
It couldn't be the cord. It couldn't be the simple pass through. And to be fair, we did check that. That was the first check we did. Hey man, is the ground support equipment on? Okay, yeah, duh. Like the engineer looks at me like, of course it's on. Like, what do you think I am? Why would I not turn it on? We're like, okay, great. Let's just check let's just check the output of that. Like, yeah, no, that was fine. It was really this pass through that lent itself to a bigger drop, right?
That's amazing. And then, so how did everyone react? Was this like a 2-minute fix once you figured it out?
The fix was, it was seconds. Like, it wasn't seconds, but it was within 5 minutes. You just took out the pass through, found a different one with a lower gauge, and it was fine. Like so there wasn't a significant drop. We just changed out the pass through essentially. And done. The length that we went through to solve this problem baffles me to this day. Like, it's one of those problems that you're just like, I can't believe we missed that. And I think it really is exactly what you said. You're focusing on this problem that's difficult. And the second thing is glazing over something so simple. And I talk about this fishbone diagram because these are things that you should really actually check. You should write down, like, great, the ground support equipment, do we check everything in there? And not just say, like, yeah, I checked the voltage, which is just one part of it. And we just checked it off, like, okay, cool, power supply works, harness works, great. So it was a perfect storm. It was a fast schedule. The actual payload itself was complicated, and you had high emotions running, right, with the team.
Were you under time pressure to get this done?
We had a very minimal margin to get this on the rocket. So we were right up to time to integrate this vehicle to the actual SpaceX rocket. So, but yeah, we're absolutely. This is one of those things that, like, okay, great, make or break, let's go.
Yeah. And this is a context where, given the novelty of all these components and what you're building, there's not like a resource to go to or someone to call. It was just sit down and test every single assumption about how this works and what might be going on.
Yeah, exactly. Like, it's great because with rockets, right? Like, there's a baseline. You understand that rockets are a thing. They've been a thing since the days of Apollo and the Mercury program. Like, we know that. This is a novel technology that's never been built. I guess I can call a physicist and say, how does this work? We've done this, but like, no, we designed this stuff in-house. So the experts of this technology is sitting within the room. So all the experts of this refinery are here.
Yeah, you're on the edge where there's not an apparatus of monitoring, a lot more established domains. You would have logging and, a bunch of testing equipment sort of perhaps adjacent or built in for all these steps.
I mean, I wish there was like a Stack Overflow that I could search. Like,
cool. I mean, it actually really reminds me of in coding or even in just writing when you're so focused on the goal that you can repeatedly read over errors. You feel like you've read something line by line, but you've elided like what's wrong with it every single time just because it's not on your radar.
And I find that analogy interesting because you can read it over and over again, but in your head you think that that's how it's working. But if you don't work out the actual, the line of code for how it's written, then you'll never.
Was there an aspect of pacing to this? Like, you're under this time pressure, but also the kind of thing you're trying to solve, you need to go very slow and methodically.
It was important for me to remind the team that, yes, this is a very aggressive schedule and we have no margin in this, right? But at the same time, we need to solve this. Otherwise, if it doesn't work, it's pointless. I had to remind the team and myself, right, at that time too, hey, let's slow down, take some time. It's okay for us to troubleshoot this and spend, X amount of days. It's fine. Let's just do it and get it right.
So what do you think you learned from this experience? What is your takeaway?
I think the biggest takeaway for me was to not take things for granted, not just glaze over something that you believe is true if you haven't validated it, right? Making sure that all the things that you thought were the cause are actually been checked and validated, as opposed to just assuming that they are working, and to not fall under this time pressure and kind of glaze by the work, and not take those simple things for granted. So even if you are under heavy time pressure, to take a minute and pause, slow down. It's okay to do that and really assess the situation and really validate all these potential failures to get to that solution. I think that was the biggest takeaway for us is let's slow down. It's okay to slow down regardless of how fast we're moving. It's fine.
Has it come up again? Has that been applicable in your work since?
Yeah. I mean, we've kind of disseminated this forward into our kind of operational flow and mantra of for the integration and test team.
It's like a thing the team's never going to forget about a time they had to get through. Yeah.
Yeah. It so much so that every test now starts with that. Like, let's just make sure every single part of the ground support equipment, all the way up to literally the point at which the spacecraft touches this ground support equipment, is checked.
Yeah.
It is ingrained in their minds, and I think it's a great lesson to have.
Yeah. There's certainly an aspect of like, we're sending this all into space. Every last chord is as important as anything else.
Right.
What can we expect? Like, what's coming? What's next for AstroForge, and what should we be looking forward to?
Yeah, the next major milestone that we have is our first deep space launch. So the target launch date is October of this year, and it is a prospecting mission. So we're going to send a spacecraft out there to take a picture of the asteroid so we can study its surface, make sure it's the right type, and potentially and look for potential landing sites for future missions after that. If we succeed, we'll be the first commercial company to ever go out to deep space. That's a feat in itself that is just a major milestone for humanity, right? Like it's now taking it out of the government hands and now commercialized. It's very, very similar to what SpaceX said with the rocket company, or with its rockets, right? We're applying that same mentality to AstroForge. Let's commercialize what the governments have done, make it cheaper, make it more accessible, and we're very excited for that. We're working extremely hard to get that launched in October. So keep a lookout for that.
Yeah, it's going to be great. It's extremely exciting, but it's also just fascinating to think through how things like the cord are going to go into that process. It'll spring fully formed and go into deep space, but the details along the way are
there'll be a lot more problems to talk about.
Yeah, for sure. Love to think back up. Well, thanks a lot, Jose. I really enjoyed speaking with you today. It was kind of fascinating. I think we learned a lot from what for you sharing your story.
Amazing. Yeah, thanks for having me. Hopefully people learn a thing or two about slowing down, even though you're supposed to move quickly.
Yeah. Great.
Thank you.
Thanks for watching this episode of HiBit. I'm Brett Gibson, managing partner of Initialized Capital. Our next guest is Ethan Feldman, co-founder and CTO of Talos, a startup that provides the infrastructure and tools to trade digital assets for a variety of Wall Street institutions.
What we wanted to do is bring that same level of institutional reliability and quality of trading systems into crypto. 30 years of electronification in the finance industry, we're trying to go through in 5 years. There were so many interesting failure scenarios here, and you have to get all of them right for this to work correctly. It's a constant struggle. There's no easy answer here, but it's critical to figure out. Long-term, all assets become digital assets. So it's all the under the iceberg stuff that differentiates a trading system like ours.
HiBit is produced by Initialized Capital. Our videographer and editor is Jordan Burns. Candy Chang is our showrunner. And I'm your host, Brett Gibson. Thanks for listening.